Welcome. In the next few sessions, we will be looking at 3 different optimization software. We will be starting with MATLAB optimization toolbox. So, it can be used to solve linear programming, mixed integer linear programming. It has inbuilt functions to solve nonlinear programming problem, and it can solve mixed integer nonlinear programming problems. Right. To the best of our knowledge, there is only one function in MATLAB which can solve mixed integer nonlinear programming problem. Again, over here it can solve mixed integer nonlinear programming problems provided they do not have equality constraint. So, that is the restriction that MATLAB has with respect to solving mixed integer nonlinear programming problems. Right. We will also be looking into GAMS. Right. So, GAMS can be used to solve linear programming problems, mixed integer linear programming problems, nonlinear programming problems, mixed integer nonlinear programming problems, and there are various other types of problem which it can solve, but as part of this course we are only classifying an optimization problem to be one of these 4, right. So, GAMS can be used to solve any of them. Right. IBM iLog Simplex Optimization Studio can be used to solve linear programming as well as mixed integer linear programming problem. It also supports quadratic programming. In addition, it supports what is called as constraint programming. So, this constraint programming is an optimization technique, right. So, constraint programming is not to be confused with constraint optimization. So, when we say constraint optimization, it means there are constraints, right. So, a linear programming problem can have constraint, a mixed integer linear programming problem can have constraint. Similarly, nonlinear programming and mixed integer nonlinear programming problems can also have constraints, right. So, when we say constraint optimization, we are specifying something about the structure of the problem, that the problem has constraints, whereas this constraint programming is actually an optimization technique, right. So, to the best of our knowledge, there are no inbuilt functions in MATLAB which can be used to solve problems using constraint programming. Similarly, to the best of our knowledge, GAMS does not seem to have anything on constraint programming. Again, remember, these are softwares which are continuously being developed, right. So, you can always go and have a look at their websites to see if they also include solution using constraint programming. So, we have chosen these 3 software for various reasons. So, for example, MATLAB optimization toolbox is available free of cost as part of this course, right, and MATLAB is more commonly available in many of the institutes, right. So, that is why we have chosen to include MATLAB optimization toolbox. So, IBM iLog Simplex Optimization Studio, for academic purposes the full version can be downloaded. So, it is available as part of IBM iLog academic initiative, right. So, and on top of that, it is the only software which supports constraint programming. Again, as part of this course we have not looked into constraint programming, but still we are talking about constraint programming because we want to know that there is something called as constraint programming, and you can go and explore on your own, right. This GAMS, if you see, it is the only software which can solve linear programming problem, mixed integer linear programming problem, nonlinear programming problem, and mixed integer nonlinear programming problem, right. So, that is why we have included GAMS, right, though it does not support constraint programming, right. So, based on the popularity, availability, and its ability to solve problems, we have chosen these 3 different optimization software. As far as accessibility is concerned, MATLAB optimization toolbox is available to you. This can be freely downloaded for academic purposes, right. So, GAMS can be downloaded from their website, right. So, you can download the demo version. So, demo version works for a limited number of variables and constraints, right. So, this GAMS is essentially a modeling language. So, this GAMS can be used along with Neos solver, right. So, we can model the problem using GAMS and then upload the code in Neos solver, right, and we can upload the code into Neos solver and get the solution, right. So, this Neos solver comes without any type of charges, right. So, in that sense all these 3 software are available to you, right. We will start with MATLAB because we presume that you have been able to install MATLAB, which was given to you as part of this course, right. Then we will subsequently move on to these 2 software. By the time we complete MATLAB, we expect that you have already installed GAMS and IBM iLog Simplex. So, now we will move on to the inbuilt functions of MATLAB which can be used to solve different types of optimization problems. MATLAB has a large number of inbuilt functions. We will be seeing a few of them, right. So, whatever we are going to discuss is based on MATLAB 2019A, right. So, the first function that we will be looking at is linprog. In linprog, the objective function has to be linear, the constraints have to be linear, it does not support nonlinear constraints, and it does not support integer variable, right. So that is nothing but a linear programming problem. If you have a linear programming problem, then linprog can be used to solve that problem, right. So again remember, linprog is not the name of any algorithm, right. So linprog is the name of a function, right. So with that function we can use any of these three algorithms. Dual simplex or interior point legacy or interior point method can be used with this function linprog to solve linear programming problems, right. So by default dual simplex is what is selected. If you want to override the default option and if you want to solve by any of these two methods, it can be done. So we will show you one example wherein we can change the default settings of any of this function, right. The second function is int linprog, right. So as the name indicates, linprog, so the objective function has to be linear, the constraints have to be linear, it does not support non-linear constraints, it can have integer variables, right. So here we are talking about mixed integer linear programming problem. Some variables can be integer, some variables can be continuous, right, but the objective function as well as the constraints are linear, right. So if we have a mixed integer linear programming problem, we will be solving it using int linprog. So for MATLAB's int linprog, it uses the branch and bound method. Then we have quadprog. So this is for solving quadratic problems or QP problems in which the constraints need to be linear, the objective function can be quadratic, it does not support nonlinear constraints, it does not support integer variables, right. So again there are two algorithms which can be used to solve quadratic programming problem. One is interior point convex method, the other is truss region reflective. So the default option is interior point convex method. Then we have these two functions fmin unc and fmin search, right. For both of these functions, this is for unconstrained optimization problem, right. So no constraints are allowed, no linear constraints, no non-linear constraints, no linear constraints, no non-linear constraints, and integer variables are also not allowed. The objective function can be non-linear. So for fmin unc, the two methods which are available is quasi-Newton method, which is the default method, and it also has truss region method. Whereas for fmin search, the underlying algorithm is Nelder-Mead simplex method, right. So fmin unc is suitable for continuous differentiable unbounded problems, right. So there should not be any bounds also, right. Whereas fmin search can be used for solving non-differentiable discontinuous unbounded problems. So both of them fall under nonlinear programming but unconstrained nonlinear programming. The other widely used function is fmincon, right. So fmincon can support linear constraints, nonlinear constraints and nonlinear objective function, right. It has these 5 methods: interior point default, truss region reflective, SQP, SQP legacy and active set, right. So this is a gradient based method, right. So the objective function and constraints are continuous and should also have continuous first derivatives. In those cases we can use function fmincon to solve nonlinear constrained optimization problem. So here also we have written NLP, right. So but here constraints are allowed, whereas in these two constraints were not allowed. The other function that we have is pattern search in MATLAB, right. So it can also support linear constraint, nonlinear constraint. It cannot handle integer variables. The objective function can be linear or nonlinear. The underlying algorithm is pattern search, right. So this pattern search can be used to solve single as well as multi-objective problems, right. Though multi-objective optimization is not part of this course, we will just show you how to solve one multi-objective optimization problem using pattern search, right. So here also it is a nonlinear programming problem, right. So if there are integer variables, nonlinear constraints, it cannot solve it. Even if everything was linear and if there is at least one integer variable, then again pattern search cannot be used to solve those problems, right. So it supports only nonlinear programming, no integer variables. So far whatever functions we have seen, only this int linprog supports integer variables, but again there the constraints and the objective function has to be linear. Other two functions which we will be looking is particle swarm. So this is based on particle swarm optimization, which we have already discussed in this course, right. And there is another technique called as simulated annealing, right. So the function for that is simul anneal BND, right. So both of this can be used to solve nonlinear problems, but they do not allow for any constraints. Both of them are for unconstrained optimization problems, right. So it does not support integer variable. As I said, particle swarm is based on particle swarm optimization, simul anneal BND is based on simulated annealing, right. So both of this algorithm is again restricted to solving single objective optimization problem. and then we have the inbuilt MATLAB function GA, right. So, here it can support nonlinear objective function, it can support linear constraints, nonlinear constraints as well as integer variable. So, the underlying algorithm is genetic algorithm, which we have previously seen in this course, right. So, it can solve single as well as multi objective optimization problems, right. So, if we are to use multi objective optimization, then the function name is GA multi OBJ. For single objective, the name of the function is GA. Similarly, here in pattern search also, pattern search as such supports only single objective, but the algorithm pattern search can be used to solve multi objective problems using this function Pareto search. So, if we see, genetic algorithm is able to support integer variables, linear constraints as well as nonlinear constraints, right. So, it can solve mixed integer nonlinear programming problems as long as the constraints are inequalities, right. It cannot support integer variables as well as equality constraints. If there are no integer variables, it can support equality constraints, but if there are integer variables, it cannot support equality constraints, right. So, we will be looking into these 10 functions, right. There are few additional functions which we will list out at the end. So, we expect that you look at the help of MATLAB and try to use them as and when necessary, but for this course we will just demonstrate the working of these 10 functions. Again, remember, we have not looked into many of these algorithms over here, right. So, we have only looked at particle swarm optimization, genetic algorithm, and we will be looking at simplex method, right. But otherwise, we have not looked into how is the underlying algorithm performing, right. So, there are various courses under NPTEL itself which covers many of these algorithms, right. So, if you are interested, you can go and have a look at those videos. Now, we will look into these functions which we have selected as part of this course, right. But to begin with, we will discuss linprog and intlinprog. So, in this session, we will be looking at how to solve linear programming problems using MATLAB. So, when we say linear programming problem, the objective function has to be linear. There can be equality as well as inequality constraints, but they need to be linear, right. Similarly, there can be bound constraints as in the decision variables are restricted between a lower bound and an upper bound. The MATLAB function to solve linear programming problem is linprog, right. So, linprog has been there in MATLAB for quite some time. Let us look into a linear programming problem. So, in this problem, there are 3 cities, city 1, city 2, city 3, right. So, there is a plant which is being set up, right. So, it is to be decided as to how much stream that which is coming out from city 1, city 2 and city 3 is to be treated, right, such that a certain amount of pollutant is removed, right. If we process, let us say x1 amount of stream from city 1, then the amount of A, which is a pollutant, that we can remove from that stream is 0.1. The amount of B that we will be able to remove by processing x1 amount of stream coming out of city 1 is 0.45 into x1. Similarly, these values have been given for city 2 and city 3, right. So, this is, let us assume that we will be processing x2 and let us assume that we will be processing x3. So, this is not known. So, the question is how much of stream coming out of city 1 has to be processed, how much of stream coming out of city 2 has to be processed and how much of stream coming out of city 3 has to be processed, right, given this is the pollutant content, right. So, to process 1 ton of stream which is coming out of city 1, it requires $15, whereas it requires only $10 to process 1 ton of stream coming from city 2, and it requires $20 to process 1 ton of stream coming from city 3, right. So, we need to decide on how much from each city has to be processed such that the total cost is minimum, right. There are 2 constraints, at least 30 tons of pollutant A has to be removed and 40 tons of pollutant B has to be removed. So, if we assume that x1 is the amount of waste treated from city 1, x2 is the amount of waste treated from city 2 and x3 is the amount of waste treated from city 3, right, and if this is the cost, right, $15, $10 and $20. So, the total cost that is required is 15x1, because for processing 1 ton of waste from city 1 we require $15, right. So, if we process x1 quantity, then we require 15x1, similarly 10x2 and 20x3. So, the total cost is 15x1 plus 10x2 plus 20x3, right. So, this is the total cost. So, now this cost has to be minimized, right. If you think about it, x1 is equal to 0, x2 is equal to 0, x3 is equal to 0 gives a cost of 0, right. Since x1, x2, x3 cannot take negative values, the lowest values that they can take is 0, right. So, the optimal cost is 0, right, but then that will not ensure this removal, that 30 tons of A and 40 tons of B should be removed, right. So now we need to include constraints such that this phenomenon is captured. So if we treat x1 quantity of waste coming from city 1, the total amount of A that we are removing is 0.1 x1. The total amount of A which we are removing by processing x2 quantity of waste from city 2 is 0.2 x2. Similarly 0.4 x3. So this is the A that can be removed if we process x1 from city 1, x2 from city 2 and x3 from city 3. So it is said that we need to remove at least 30 tons. So that is why we have this greater than equal to symbol, right. So it can be greater than 30 or it can be equal to 30, it need not be exactly equal to 30, right. So writing this as point x1 plus 0.2 x2 plus 0.4 x3 is equal to 30 is not correct, right. It does not capture what is required in the problem. It says we need to remove at least 30. If we are removing more than 30, that is not a problem, right. So this constraint captures only the reduction in pollutant A. So the reduction in pollutant B similarly can be done by 0.45 x1 plus 0.25 x2 plus 0.3 x3 should be greater than or equal to 40. Again the problem requires that at least 40 tons be removed. So these two are constraints. So here if we see, the objective function is linear, right, both the constraints are linear and the variables are continuous variables. So x1, x2, x3 are continuous variable. The lower bound is 0, right. So it does not make sense if we say that we will process minus 5 tons from city A, right. It has to be a positive quantity, right. So that is why we have this x1 comma x2 comma x3 is greater than or equal to 0. So now we have continuous variables, all the 3 variables are continuous and we have 2 constraints which are linear, right, and the objective function is also linear. So this problem if you classify, it will be linear programming. So we will use the MATLAB function linprog to solve this problem, right. So if you do help space linprog on the command window, it will give help on the function. So linprog requires the problem in this format, right. So the constraint should be in this less than equal to form, right. If we have greater than equal to form, it cannot be directly be given to MATLAB, right. It has to be converted into less than equal to form, right, and it can solve only minimization problems, right. So if we have a maximization problem, we have discussed how to convert it into a minimization problem, right. We need to convert the maximization problem to minimization problem and only then we will be able to use MATLAB to solve it, right. So we will look into what is this A equality and B equality with the example that we have considered. LB and UB are the lower and upper bound of the decision variables, right. So right now what the problem that we had was this one, minimize z is equal to 15x1 plus 10x2 plus 20x3, and these two were constraints which had this greater than or equal to symbol. First we need to convert this problem into this one wherein the constraints are in the less than equal to form, right. If the constraints are in the less than equal to form, only then we can use MATLAB to solve it, right. So that is why we multiply by a minus sign on both the sides and we have these two constraints, right. So now this modified problem, right, which is exactly the same as the original problem, but it is in a format that is required for solving using MATLAB. So for this problem we need to provide the coefficients of the decision variable in the objective function. In this case the coefficients are 15, 10 and 20, right. So we will define that as a variable z. This variable z is what is to be given, or this variable f, right. So it is just a different variable name that we are using, right. So this z is the coefficients of the decision variables in the objective function, right, and this A is the coefficient matrix of the inequality constraints, right. A and B are two variable names, right. They should contain the coefficients of the decision variables in the constraints, right. So for example the first constraint is minus 0.1 x1, minus 0.2 x2, minus 0.4 x3, right. The second constraint is minus 0.45 x1, minus 0.25 x2 and minus 0.3 x3. So this A contains the coefficient matrix, right, whereas the vector B is the right hand side of those two constraints. So B is minus 30 and minus 40. The lower bound for this problem is 0 0 0, right. So here you need to remember that we need to first decide how we are going to arrange the variables, right. So when we write this, we have implicitly assumed that our variables are arranged in x1, x2, x3, right. It is not necessary that we always arrange like this, we could have even arranged it as x2, x1 and x3, right. If we have done that, then this A matrix should be appropriately rearranged, right. So here the assumption is that A into x is less than equal to B, right. So A into x is less than equal to B. So x, if we do not consider x1, x2, x3, if we consider x2, x1, x3, this A matrix will appropriately change, right. First fix the order in which we are going to arrange the decision variable and then supply coefficients, right. So for the function linprog, the input that we need to give is this variable z, right. So which should contain the coefficients of the objective function, right. So it can be any variable. So for example, instead of z over here, I could have used y and I should use the same variable y, right. The first variable should contain the coefficients of the objective function, right. The second variable and the third variable represent the inequality constraints. The second variable should contain the coefficient matrix of the inequality constraint. So the coefficient of the inequality constraints for this problem is given over here, right. So that is A. B is the right hand side values of the inequality constraints, right. So in this case we have minus 30 and minus 40. So B will be minus 30, minus 40. If we had equality constraints, just like we derived the coefficients of this inequality constraint, we can also derive the coefficients of equality constraint. So that has to be given in subsequent variables, right. Then we need to provide the lower bound, we need to provide the upper bound, and then we need to provide the options, right. Options is usually provided when we want to override the default options of linprog. So remember, all functions require some kind of user defined input, right. If nothing else, then you need to at least select which is the algorithm that linprog is going to do, but for all of them MATLAB by default selects some value. If we want to override the default value, we can use this options to do that, right. But right now we will not be looking into this options, right. So but that can be done, right. The output would be the decision variables, right. So here for this problem we have x1, x2, x3. So this x will be a vector of 1 by 3. Fval is the value of the objective function at the optimal decision variable, right. So what we get x, if we substitute those values of x in this objective function, what will be the value of the objective function, that can also be obtained from this linprog function, right. So the second variable would be fval, right. The third variable exit flag tells us as to when the algorithm stopped, what is the reason for it stopping, right. So exit flag will give us that, right. This variable output is actually a structure. It will give a lot of information including number of iterations, what was the algorithm used, why did the algorithm stop, which is there in this exit flag, that also it will give, right. It also gives what is called as Lagrange multiplier or shadow prices, right. So this gives additional information about the solution of the problem, right. As of now, just know that we will be getting these 5 outputs, right. So analyzing these two is straightforward. X is the solution which linprog has been able to get, right. Fval is the objective function value at that point, right, and exit flag is the reason for why it is stopping. Output will contain additional information about the solution, right, and this lambda is the Lagrangian multipliers or the shadow prices. We have written this x over here below min to indicate that x is the decision variable, right. This is the script file which can be used to solve the problem, right. So CLC and clear, you know, we are defining the lower bound zeros of 1 comma 3. So it will create 1 row 3 columns because we have 3 variables, right. We do not need to create UB because for this problem UB is infinity. We need to define this A matrix. So that is what is being done over here, right. So A is equal to within square brackets minus 0.1, minus 0.2, minus 0.4 semicolon. So that goes on to the next row, minus 0.45, minus 0.25 and minus 0.3, right. So that will help us to define A, and this B is the right hand side vector. So B is equal to minus of 30 space 40 or transpose, or we can remove this transpose and just say minus 30 semicolon 40, right. And this Z is the vector 15, 10, 20, which is the coefficient of objective function. So anything that starts after this percentage symbol are comments, right. It is not required for solving the problem. So linprog, we are accessing the function linprog. The order is important. So the first one should be the coefficient of the objective function. The second variable is coefficient matrix of the inequality constraints. The next one is the right hand side vector of the inequality constraints. Since we do not have equality constraints, we do not have a coefficient matrix and we do not have a right hand side vector for equality constraint. So, this is empty bracket, and we do have lower bound, right. So, lower bound is to be supplied, right. So, here if you see, we have not given comma ub comma options, right, because ub for this problem is infinity. As of now, we are not changing the default options by which this linprog will solve this problem, right. We are solving with default options. So, that is why we have not given lb comma ub comma options, right. So, when we are solving this, we are seeking these 5 values: the decision variable, the value of the objective function, the reason why it is terminating in exit flag, output, and the shadow prices. So, if we do that, this is what we will get. We will get the decision variable 7.6923, 146.1538, 0. So, this means x1 is 7.6923, x2 is this, and x3 is this, because this is the way in which we had arranged the variables, right. If our x was x2, x1, x3, right, then this z would have not been 15, 10, 20, it would have been 10, 15, 20. Similarly, this a would have changed, right. So, in that case, the answer which we would have received is 146.15 would have been the first value, right. So, the order in which we are supplying the input has to be consistent for the constraints as well as the objective function and the lower and upper bound. So, the solution that we obtain will be in the same format, right. For this decision variables, the value of the objective function is 1576.9231, right, and this lambda will be a structure, right. The structure will contain 3 values: the lower, upper, and inequality. So, if we say lambda dot lower, we will get 3 values. If we say lambda dot upper, we will get 3 values. If we say lambda dot ineq lin, we will get 2 values, right. So, there are 3 values over here and over here because we have 3 decision variables. There are 2 values over here because we have 2 inequality constraints, right. So, we will see how to interpret this, but as of now we are just seeing how to access the values, right. Once we access the values, we will talk about how to interpret it, right. So, in this case, you need to remember that these are just variable names. It need not be x, fval, exit flag, output, lambda. It can be any 5 variable names, right, but lambda would be a structure, output will also be a structure, exit flag will be a scalar, fval will be a scalar because it is the value of the objective function, and the size of x is going to be the same as size of our optimization problem or the size of lower and upper bound. The previous problem which we solved using linprog did not have equality constraint, right. So, we will look at an example wherein we have an equality constraint, right. So, the objective function that we have over here is x1 plus 2x2 minus 3x3, right. So, this is an optimization problem involving 3 variables. The decision variables are x1, x2 and x3, right. We have 2 inequality constraints, right, both of them are linear, right. So, x1 plus 2x2 is less than equal to 3, x2 plus x3 is less than equal to 2, and we have one equality constraint x1 plus x2 plus x3 equal to 4. The lower and upper bounds are as given over here, right. So, the variable x1 has a lower bound of 0 and an upper bound of 5, variable x2 has a lower bound of minus 1.5 and an upper bound of 3, x3 has a lower bound of 0 and an upper bound of 2, right. So, this is the problem that linprog can solve. So, here we will define x to be x1, x2, x3, right. So, the coefficient of x1, x2, x3 is 1, 2 and minus 3. When we have z into x, we will get x1 plus 2x2 minus 3x3, right. So, these 2 constraints we need to find out the coefficient of x1, x2, x3, right. So, first equation if we see 1x1 plus 2x2 plus 0x3 is less than equal to 3. So, that is why we have 1, 2, 0 over here, and the right hand side is 3. Similarly, the second equation is 0x1 plus 1x2 plus 1x3, 0, 1, 1, and then this right hand side value is 2. This is a, this is b, right, and then we define another variable, right, aeq, right, for equality constraint. So, we have only one equality constraint, right. So, here the coefficient of x1, x2, x3 is 1, 1, 1. So, we have 1, 1, 1 over here, and the right hand side value is 4. So, we have 4 over here. So, LB is used to define the lower bound. So, the lower bound is 0, minus 1.5 and 0, and the upper bounds are 5, 3 and 2. So, this is the upper bound, right. So, now we have transformed this problem to the format required by MATLAB, right. So, again remember it only supports less than equal to constraint. So, if we have a greater than or equal to constraint, we need to multiply by a minus sign. Similarly, if we have equations like this f1 x1 plus 2 x2 minus 3 is less than equal to 0, then we need to take this minus 3 to the right hand side. Similarly, for equality constraint, if it is x1 plus x2 plus x3 minus 4 is equal to 0, then we need to take this minus 4 to the right hand side, because that is the format which is required for linprog. So, here we define CLC nclear to clear the command window and MATLAB workspace. We define Z, right, as 1 2 minus 3, A and B as defined over here, right. Similarly, A equality and B equality, this A equality and B equality, the lower bound and the upper bound. So, the lower bound and the upper bound, right, and then we supply that information in the specified order, right. So, the first value has to be the coefficient vector, the second one has to be the coefficient matrix of the inequality constraint, third one has to be the right hand side value of the inequality constraint, fourth and fifth one is about the equality constraint, lower bound and then upper bound. Here we are solving with the default options of linprog, so we are not giving any options. So, the output we expect from this function is the values of the decision variable, right. So, in this case it will be 3 values, because we have 3 decision variable. This will be a scalar value, because this is the value of the objective function at this point. So, that would be a scalar. Exit flag again will be a scalar, it will tell us what is the reason for termination of linprog. Output is a structure, right, which will have several fields which will tell various information on the solution of this problem using linprog. And then we have the Lagrangian multipliers, right. So, Lagrangian multipliers in this case, since there are 3 decision variables, so we will have lambda dot lower and lambda dot upper, each of this will contain 3 values, because there are 3 decision variables. Lambda dot inequality will contain 2 values, because we have 2 inequality constraints, and lambda dot eqlin, right, will contain only 1 value, because we have only 1 equality constraint. If we have 10 decision variables, 2 inequality constraints and 5 equality constraint, right. So, then lambda dot lower and lambda dot upper would each would have 10 values, right. Lambda dot inequality would have 2 values and lambda dot equality would have 5 values. This lambda denotes the Lagrangian multiplier or shadow price, right. So, we will discuss on what is the significance of this Lagrangian multipliers with an example. Now that we have seen how to solve a linear programming problem using linprog, let us move on to intlinprog. So, intlinprog is used to solve mixed integer linear programming problems. It can solve problems in which some of the decision variables are integer and some of the decision variables are continuous, right, but still the objective function and the constraints need to be linear. So, in integer linear programming, as you might remember, the objective function is linear, the constraints both it can support linear equalities and linear inequalities, right, and it can also have bound constraints as well as integer variables, right. So, the function that we will be looking at is intlinprog. So, this is a problem which we have previously discussed, the paint problem, that these are 2 raw materials M1 and M2, and 2 types of paints can be produced, interior paint and exterior paint. So, these 4 values indicate the amount of raw material M1 and M2 required for manufacturing paint 1 and paint 2, right, and the availability of raw material M1 and M2 is 24 and 6. The profit realized by selling 1 unit of exterior paint is 5, the profit realized by selling 1 unit of interior paint is 4. So, we need to decide on how many units of exterior paint and how many units of interior paint need to be manufactured, so that we maximize the total daily profit, right. There is an additional constraint that maximum daily demand for the interior paint is 2 units, and the daily demand for interior paint cannot exceed that for exterior paint by more than 1 unit. So, we had previously modeled this, right. So, we will not get into it again. So, these are our constraints, right. We have 3 constraints and 2 decision variables, right. In this case, both the decision variables are integer. We want to determine the number of units, right. So, 5.3 units is not a valid answer, it has to be an integer. This x1 and x2 has to be an integer, right. So, the lower bound is 0 for both the variables, whereas the upper bound for x2 is 2. There is no direct upper bound for x1. The bound for x1 will be determined by these constraints, right. So the MATLAB function which we are going to use here is int.linprog, right. So similar to linear programming, we need to put it in the appropriate format, right. So this is a maximization problem, and int.linprog, similar to linprog, solves only minimization problem. So we need to multiply this objective function by a negative sign, and we need to only supply the coefficients, right. So the coefficients are -5, -4, right. So when we write the coefficient in this order -5, -4, we have decided that our x vector will be x1, x2. That's when zx will give us -5x1, -4x2. Similarly, we need to determine the coefficients of the inequality constraints, right. So here we have 3 inequality constraints. So 6, 4, 24, 1, 2 and 6, 1, 2 and 6, right. This x1 has to be taken to the left hand side because MATLAB supports constraints of the form ax is less than equal to b. So here we need to take x1 to the left hand side. So we will have -x1 plus x2. So -x1 plus x2. On the right hand side we will have 1, which is over here. The lower bound for both the variables are 0, 0, and the upper bound for the first variable is infinity. So infinity in MATLAB is given by INF, and the upper bound for the second variable is 2. So this is what int.linprog solves, right. So minimization problem, we need to provide the constraints in this form, right. So it does not support a constraint of the form greater than or equal to, it supports only of the form less than or equal to, and we need to supply the lower and upper bounds, right. So if you compare this int.linprog with linprog, right. So this is for int.linprog. Previously we had discussed linprog, right. So if you look at it, it is similar, except for the fact that we also need to indicate the variables which need to take only integer values, right. So that is the difference between linprog and int.linprog. So here we have converted that maximization problem into a minimization problem, right, and we have determined this input over here z, a, b, lb, ub. So a, if you see, the coefficient of this is 6, 4, 24, right, 6, 4 and 24. The second constraint 1, 2 and 6, 1, 2 and 6. Over here -1, 1, -1, 1, and again 1 on the right hand side. The lower bound of both the variables are 0. So that is why we have a 0. The upper bound is infinity for the first variable, right, and the upper bound for the second variable is 2. That is what we have given, right. So here this transformation you might be knowing, right. So this is a maximization problem that is converted into a minimization problem because int.linprog can solve only minimization problems, right. And over here if you see, on the right hand side we are expected to have only constant coefficients, right. So over here we have a constant coefficient, over here we have a constant coefficient, but over here we do not have a constant coefficient. So x1 on the right hand side has to be taken to the left hand side. So that way we converted this problem into the standard format, right. So the input to int.linprog is similar to linprog, right. So this is the name of the inbuilt function int.linprog. Remember, it is in lower case. So we need to give the variable which has the coefficient values of the objective function, right. We will come to this intcon in a while, right. So this a, b is the coefficient matrix of the inequality constraint, b is the right hand side vector of the inequality constraint, a equality is the coefficient matrix of the equality constraint, b equality is the right hand side of the equality constraint, lower bound, upper bound of the variables, x naught is the initial guess, right. So for any problem, if required, we can supply the initial guess. So that is the name of a variable x naught, right. And additionally we can give this options if we want to override any of the default options of int.linprog. So much of it is similar to what we discussed for linprog, right. So only difference is this intcon. So over here for the intcon, we need to specify the indices of the variables which are integer. Let us say I have 3 variables x, a, b and f. For some reason, let us say I have these 4 variables and I decide to arrange in this format a, f, b, x, right. These are 4 decision variables in our optimization problem, and out of these 4 variables, let us say a and x are integer variables, right. So we have 4 decision variable x, a, b, f. In this, x and a are integer variables, okay. And let us say we have decided to arrange the variables like this, right. So first we have to decide the way in which we are going to arrange the decision variable, only then we will be able to write coefficient matrix. So for example, over here this -5 -4 captures this 5x1 plus 4x2 if and only if x is x1 and x2. If it is x2 and x1, then it is minus 5x2 minus 4x1, which is not the case that we have. So let us say we decide to arrange the variables as a, f, b, x. Now in this, x and a are integer, right? So what is the position of x? So the position of x is 4 and the position of a is 1. These two are the index of the two decision variables which are integer. So in this case, int con has to be 1, 4. So this will help the inbuilt function MATLAB to realize that the first variable and the fourth variable are integer. So the first variable is a and the fourth variable is x, right? So that is what this int con indicates. It indicates the indices of the integer variables. So now let us look at the script file for this problem, right? So this is the problem which we have. We do not have any equality constraint. We are not going to give any initial guess, right? So you know what is CLC and clear, right? So we define the variable z as minus of 5 and 4, right? So this is the coefficient of the objective function, and then we use this variable a and this variable b to define these values, and then we use the variable lb and ub to define the lower and upper bound which we have for this current problem. Remember, all these are names of variables, so it can be anything, and appropriately that variable name has to be used over here, right? So it's not necessary that this variable should always be int con. Let's say this variable is k, right? Then we'll have to appropriately use k over here, right? So here in this case we have two variables, both of them are integers, right? So here we give 1 and 2. So far we have defined the necessary variables which can help us to define our problem, right? So now we are solving it with intlinprog. So for intlinprog we need to provide z, int con or k, a, b. We do not have any equality constraint, right? So both of this would be empty brackets, right? And then we need to give lower bound and the upper bound. So beyond upper bound we don't need to give anything because we do not have, since we do not have an initial guess in this case, we don't need to give empty brackets, because beyond ub we are not using anything, right? Over here we had to give this empty bracket because we are still using this variable lb and ub, which can be defined only after the equality constraints are defined, right? So that's why we were forced to give this empty brackets over here. So the output of this function would be x and fval. The size of x will be the same as the size of lower bound or the upper bound, right? So we have two variables in this case, so x will contain two values. The first value will be x1, the second value will be x2, because that was the convention we had followed to define all these values, right? So all these values are correct only if x is in this format, right? So the result will also be in the same format. So there will be two values of x. The first one will correspond to the optimal value of x1 and second one will correspond to the value of the objective function at this particular x, right? So in this case we get x as 4 and 0, right? So that is x1 is equal to 4 and x2 is equal to 0, right? So our objective function was 5x1 plus 4x2. This was to be maximized, right? And what we did was minimize minus 5x1 minus 4x2, right? So if you substitute this 4 and 0 in this expression, because this is what was given to intlinprog, so what we will get is minus 20. So that is nothing but this fval, right? So but our problem was maximization, right? So the profit is whatever value we need to get, we need to multiply it by a minus sign, because we have converted the maximization problem into a minimization problem. So now the answer whatever is given has to be multiplied with minus 1 to get the objective function value of the maximization problem. So in this case it will be minus of minus 20, so which is 20, and the amount of exterior paint we need to generate is 4 and the amount of interior paint that we need to generate is 0, right? You can check this solution also satisfies the constraints, right? So over here we did not use exit flag, right? So what we could have done is, instead of just stopping with x comma fval, we could have given x comma fval comma exit flag, right, equal to this right hand side as such, right? So in this case it would have given us the value of x, the value of fval, and also it would have given us a number with which we can find out the reason for termination of the algorithm. So as and when intlinprog terminated, right, what was the reason for which it terminated? Did it find the optimal solution and did it terminate, or did we reach any resource limitations, or it terminated for any other reason, right. So that can be determined using this exit flag. You can also give x comma fval comma exit flag comma output. So again, if you look into this output variable, it would be a structure, it would contain additional information about the solution of this problem using int linprog. So we leave it to you to explore what is exit flag and what is the information that you get from output. So for this problem, let us say we had an initial guess of, let us say 3 comma 2. So then what we could have done is, we could have said g is equal to 3 and 2, and over here lb comma ub comma g we could have given, right. So this way you can use int linprog to solve a mixed integer linear programming problem. So the example which we showed is actually a ILP. We had two variables, both of them were integer variables, but it is not necessary that all the variables need to be integer for us to use int linprog. Even for this problem, let us say x1 was not integer, only x2 was integer, right. So in that case what we could have done is, this int con we could have defined it as just 2. So in that case x1 will be treated as a continuous variable between 0 and infinity, and x2 would be treated as a integer variable which can take either the value of 0, 1 or 2, because the lower bound over here is 0 and the upper bound over here is 2. So the question is, what would have happened if we had solved this problem with linprog, right, and whatever values we had got for the decision variables, what if we had rounded it off. So let us solve the same problem by linprog, right. So linprog, so remember we have been told that x1 and x2 are integer variables, right, but still we choose it to solve with linprog. We are under the assumption that we can solve it using linprog, and then whatever values we get, we will round it off, right. So let us say x1 if we get 2.3 and x2 if we get 2.9, then we will round off the solution as 2.3 to 2 and 2.9 as 3. So very often this is a misconception that this can be done, right. So for this problem, let us see what will happen if we solve with linprog, right. So this piece of code you will be able to understand. Just instead of int linprog, we are using linprog, and over here we are not defining that int con, right. So otherwise we would have given the int con over here between z and a. So here we are not giving, so for linprog that is not required, right. So if we solve this problem, right, so the value of x1 we would get is 3 and the value of x2 is 1.5, right, and the objective function value is minus 21. So minus 21 is actually better than minus 20, right, which we had got using int linprog, right. So only thing is that these two values are not integers, so we cannot use these values. So let us see what will happen if we round this off. So let us say we decide to seal this solution, right, 3 and 1.5 we decide to seal this solution. So if we seal this solution, we will get 3 and 2, and the objective function value corresponding to it would be minus 5 into 3 minus 4 into 2, right. So this if you work out, it will come out to minus 23, right. So by sealing we get a better solution, right, but the question is this solution a feasible solution? Does it satisfy all the constraint, right. So what we can do is, we can substitute this value of x1 and x2 into these constraints, right. So what we can do is, we can find out this ax minus b. Remember our constraint is ax is less than equal to b. Now we have x given by this 3 2, we have this a, so we multiply a with x, minus b should be less than equal to 0. So this condition has to be satisfied, but if you plug in this x with this a matrix and find out ax minus b, you will see that you will get 2, 1 and minus 2. So the all these three values are supposed to be less than equal to 0, but only the last value is less than equal to 0. The first two values are positive numbers, right. So that means this solution 3 and 2, which has a better objective function, right, is actually an infeasible solution, right. So sealing the solution can give a better value of the objective function, but then it may lead to infeasibility. So here the question is, we seal the solution, what happens if we take the floor of the solution? So the floor of the solution is 3 and 1. If we calculate the objective function for 3 and 1, that is minus 5 into 3 minus 4 into 1. So this will be minus 19, right. Again we can calculate for this solution ax minus b. So in this case all the three values are less than 0, right. So this is a feasible solution, but it has an objective function of minus 19. If you remember from int linproc, we had got a solution of minus 20, right, whereas if we use linproc and then floor the solution, in this case we end up with a suboptimal solution, right. So that is why it is necessary to use the appropriate function for the problem at hand. If there are no integer variables and if there are only continuous variables, then it is better to solve it using linproc. If there are integer variables and the constraints are linear, right, then we should use int linproc, right. Sealing of the solution and the flooring the solution may either take us to a suboptimal solution or it can lead to a infeasible solution. So with that we will conclude this session. In this session we have looked into how to solve linear programming problems as well as how to solve mixed integer linear programming problems. For linear programming problems we used linproc, and for mixed integer linear programming problems we used int linproc. So we have not looked into few things such as how to change the options as well as how to interpret the lambda values. That we will be doing subsequently, as that part is common to most of the inbuilt functions which we use for solving optimization problems in MATLAB. With that we conclude this session. Thank you.